So complex structures. What you are seeing are regular grids, rectangular grids. So these rectangular grids are we have seen have that I comma j naming. That is, if we can open up the grid and name it, 0 comma 0, 0 comma 1, etc. It's a regular grid. If you cannot do that, it becomes unstructured grid. Okay. For complex geometries, either we use multi-blocking for regular grids or unstructured grids. Unstructured grids are easier to use for complex geometry. But with regular grids, we have more control over the grid. So we looked at the governing equations last class, if you remember. Have to derive the differential form of equations. So once you do that, we'll be using something called the strong conservation form or integral conservation form. Or strong conservation form, maybe it is a differential or integral. We'll come to that later. So it is very useful for doing this finite volume calculations, which is used in your ANSYS fluid software, ANSYS CFX software. They use this method. So
Sir, can you please share the screen, sir?
oh yeah, I haven't started yet. Actually, I'm just verbally, I'm talking to you. Thanks for the making. Do it all the but are you able to see the screen?
Yes, sir.
Yeah.
Yes.
So okay, great. So now we are looking at this integral conservation form of the governing equations. The governing equations are the Navier-Stokes equations, as we all know, and we saw the integral derivation last class. Right now, what is the advantage or disadvantage of integral form versus differential form of governing equation? Actually, it's an advantage. If you use the integral form of equations, they don't assume that the function you are integrating is actually continuous. Sorry, is actually differentiable. Like they should be continuous, okay, but you can have sudden jumps or even discontinuous. For example, there are shocks. Okay, so technically speaking, when you have a set of partial differential equations, continuity of the variables are assumed everywhere inherently. But when you do the integral form, you are looking at a control volume. So even if the function discontinuous inside the volume, you can integrate, piecewise integrate and add them. Correct. For example, I can I'm just revise. I mean, it will be obvious to some of you. Some of you may need some explanation. That's why I'm explaining. So for those of you, it's very obvious. Please bear with me. For example, pressure. You move along x-axis. At this point, let's say there's a shock, and inviscid shock, like what you know. What happens to pressure across shock wave? Smish, smish.
So it will decrease.
No, no. Across means when you go downstream. Upstream, you have subsonic velocity. Sorry, supersonic velocity. After a shock, you'll have subsonic Mach number. Correct? But the pressure will increase. Okay? So suppose it's a uniform flow. Pressure is so much. Suddenly, it will increase after the shock. So pressure is discontinuous across the shaft according to this formulation. If you want to apply the differential form, for example, this region, then theoretically you cannot because there's a discontinuity here. Okay, the value of pressure is the limit toward the left is only so much, the limit toward the right is so much. There's a step increase. Okay, but if you want to integrate the integral form, you have that say something is some function, not pressure, some other say something like pressure. If you want to integrate this integral p dx, for example, along the same interval, what are you doing from this point where you want to integrate to this limit? It is just the area under the curve. You can still integrate. Okay, so you can do piecewise integration. Before the shaft, you can integrate so much. After the shaft, this is the area. You can add them both and get the integral without any problem. It does not assume that, see, this formulation does not assume that the function has to be continuous. This function p has to be continuous and everywhere. It can be discontinuous and still you can integrate. Whereas if I want p and want to find dou p by dou x, this is not defined at this point. It has, right, not even continuous. So how can it have the derivative? It cannot have. Is it clear, Smish?
Yes, sir.
Okay. So the differential form, theoretically, it has a limitation. But anyway, when you're applying numerical methods, there'll always be some smearing and all those stuff. We are not talking of that now. Only from the theory mathematical point of view, we are stating that the integral forms are a little bit more stronger formulation because they allow for the presence of discontinuity inside the fixed control volume. This is known as conservation form. But the differential form inherently assumes that the flow properties are differentiable. So because differentiable, they should be continuous. This is a problem. Okay. Now, not that you cannot use the differential form, but it has inherently this uh, mathematical. What is it? I should say, in it doesn't have that capacity to handle these things theoretically. So it's a strong argument to consider that or say that the integral forms are more fundamental than the differential form. Okay, boss, differential. I don't have anything against you, but I am more fundamental. Say the integral form. Okay. So the integral forms are more fundamental than the differential form. Now, in particular, the governing Navier-Stokes equations with no source terms. Source terms means, the right hand side is zero. For example, no energy is being produced, no body forces, so right hand side is zero. So it may be written for 2 dimensions in strong conservation form in a very simple manner. This thing is very suitable for CFD. You just have dou u by dou t, where u is a matrix, or that you can call a matrix as a vector, n-dimensional vector. Okay. For example, we will look at the next one. Use the vector of independent variables, or we can also put it as a matrix of independent variables plus some function dou f by dou x plus dou g by dou y is equal to 0. Now all you have to do, this is a very simple thing to remember. Dou by dou t, dou by dou x, dou by dou y, u, f, g. Now if you, the expansions of this is just, the very small form. If you want expansion, then the abbreviation. Okay, this is abbreviation. Don't take expansion, it's here. U, the independent variables, rho, rho U, rho V, rho into E plus V squared by 2, the whole transpose, which means if I write a column vector, I have to spend an entire page for this. And for the next one, I have to go to the next page. So to put everything, I just put it in the row vector and put a transpose here. So what does dou U by dou T means? The first equation is dou rho by dou T. Means dou rho by dou T. Then what is the first equation here? For F, rho U. So that is plus dou of rho U by dou X. Second one is rho V. So plus dou of rho V by dou Y is 0. That is nothing but the continuity equation, the differential. Okay. Differential or integral. You can also put an integral outside this. Integral of the whole thing into dx dy. You can put. Or you can integrate this into dt. This integral, the whole thing. This is equal to dou f by dou y minus dou g by dou x. You can look at the proof later. So this is just a differential form we are writing. This is also a strong conservation form because we can convert it to differential form later. Let's look at differential form. The differential form can be converted to the integral form in the numerical integration. We will come to that later. Then second equation is dou of rho u by dou t. This is nothing but no x momentum equation. Dou of rho u by dou t is equal to dou f by dou x. So second term is dou of rho u squared plus p minus tau x by dou x. See that? Okay. Then third term is dou of rho uv minus tau yx by dou y is equal to 0. If you look at it and explain it carefully, you will realize that it is the x momentum equation, second terms of all this. The third term of all these things will be y momentum equation. Okay, up to this comma. So it's a two-dimensional. It's written for two dimension. In three dimension, you have similarly a little bit more. Rho w also will be there. Then finally, energy equation. This term and whatever is here will be dou by dou x. Whatever is here will be dou by dou y. So all this is succinctly put in this form: dou u by dou t plus dou f by dou x plus dou g by dou y. Okay. Is it clear? Any doubts? Yes. Rashmita, any doubt?
No, sir.
Okay, great. Anyone else? Okay, so we'll move to the next one. Yeah, we'll now move, just hop on. We will jump on to revise something. Okay, because some facts will become clearer if you revise. We are just going to apply something which we learned very, very long ago. Okay, so this is CFD method. So anywhere you use the numerical method. Anytime you use a computer, you can call this as a numerical method. Panel methods are also numerical methods. Okay, you would have learned about panel method, no, earlier.
So somewhat in aerodynamics we have learned.
Yes, yes, same thing. I'm just going to revise here quickly.
Lifting line theory.
Yeah. Yes, now we are just going to a numerical aspect. We'll just revise that just to show that it's a numerical. It's just a revision, nothing else. So 2D potential flow solutions. If you have any doubts here, just please right now you stop and ask the doubt, okay? Because later on there may not be a chance. We may be going a bit fast. So 2D potential flow, even though it is, maybe old stuff to you, if you have doubts, you just clarify now. I'll go back and read that chapter thoroughly. So in potential flow, what do we do? It's a simplification of the Navier-Stokes equation. If you assume there is no viscosity, certain terms drop off and they become Euler flow equations. That is Eulerian flow. In the earlier one, this is actually Navier-Stokes equation. If you assume this tau xy is 0, no viscosity, tau xx is 0, all these things 0, then you also assume that it is incompressible. This is 2D incompressible. Okay. So what happens? For incompressible flow, energy equation drops out. Rho is a constant. Okay. Still, it will work if you put rho inside. It behaves like a constant. Okay. So no energy equation for incompressible flow. So it becomes, yeah. Any doubts? So there are basically three equations for 2D incompressible flow. Three, they are not, algebraic equations. There are three partial differential equations. Not only that, if you want rho, you have to know rho u and rho v. If you want to know rho u, you should solve the second equation, which needs rho. The third one, you need the independence rho v. It has rho vu and all those stuff. Okay. So they are hopelessly, coupled partial differential equations. They are coupled with one another. Even coupled, you can liken them to a three unknowns algebraic equation, but they are not the same. Those are discrete things, algebraic equations, functions. These are partial differentials. Okay. So, but philosophy is same. If you have the proper boundary initial condition, if there are n PDEs and n unknowns, you can solve for that. They are well posed. But not some one of the basic conditions for solvability, let's say. So that we'll give a name for that called as well postedness. Yeah. Now this is inviscid two-dimensional flow. We assume steady state also, so that these variables do not change with time. So steady, inviscid, 2D equations are known as Euler equations. Okay. Now, if in the Euler equation, if we impose the potential condition, what is the potentiality condition? The flow is irrotational. There is a rotationality omega everywhere. Everywhere in the flow field, del cross V is 0. If you assume that condition, for many practical flows, you can assume it to be true. Not a big sin. Okay, you can get an approximate solution. So people say that, yeah, I will live with it. If you make that one more small assumption, the assumption is already there, the magic happens. See, these three non-linear equations. Non-linear means you cannot add individual solutions together. For example, if A1 is a solution which satisfies this equations, these sets of equations. A2 is another equation, another solution, two sets of equations. This coupled non-linear PDEs. If you add them, you'll get A1 plus A2. Now, although A1 is a solution and A2 is a solution, their sum need not be a solution if the PDE is non-linear. Now, the PDEs are not only non-linear, they are also coupled with each other. So, the hopes of getting analytical solution have diminished to very low levels. Unless you make further assumptions, not possible to get meaningful solution. Very, very special cases probably you can get. That is the situation for even inviscid flow with all these assumptions. Now to get a solution, you are seeing irrotationality. The magic happens then. What is the magic? By assuming that the velocity is a derivative of a potential function. The potential function is a scalar, so the derivative, the del operator on this will be a vector. Okay, so this del phi is equal to velocity. That's what you assume. No, I'm not assume. You can actually prove that the velocity can be expressed as del phi if the flow is irrotational. It can be proved. Okay, so your flow is irrotational. All these three coupled nonlinear PDEs become one linear PDE. Fantastic. Linear means if you have a solution A and solution B, then A plus B is also a solution of the equation. A plus B, if C is also a solution, A plus B plus C is also a solution. There are n number of solutions, you can add them in any fashion you want. All of them will be solution of the equations. That is the beauty of a linear PDE, linear partial differential equation. So this couple nonlinear PDEs have become in three different variables have become a linear PDE in one unknown variable phi. It's a great achievement, and that happens to be the Laplace equation. Now solutions to Laplace equations are available. Okay. So this phi is actually a scalar. Because we know the phi everywhere in the flow field, you can find the velocity everywhere in the flow field. Dou phi by dou r. R is the u component is dou phi by dou x, v component is dou phi by dou y, and so on. In simple Cartesian coordinates. Okay. So this function phi, you now can have very many elementary flows which satisfy the Laplace equation. Source flow, which is actually one source flow can visualize, there's a point or you can imagine a broken pipe underneath the water, just bubbling out through an opening in the ground. It will come out and tend to move equally in all directions. Okay, you can somewhat think of this as something like a source flow. It has no preference for direction. All directions are equally preferred, unless there is a gradient in the ground or something. Okay. So this is source flow. This is the solution of Laplace equation. Okay, but the source should have a strength. That is how much mass flow is coming out of the broken pipe per second per unit time. That will tell you the strength of the source. If more mass is coming out, it will move out faster radially. If less is there, it will move out slower. The opposite of this you can say is the sink, where you can assume that there is a pit towards which all fluid is flowing. From in a rain, when it is raining, there's a hole. All water is rushing towards the pit and going somewhere down the drain. Okay. Or in your bathroom sink, there is a sink. What you call as a sink is a sink. Because if you fill it with water, suddenly remove the plug and open the sink, all water will tend to flow into the sink. Streamlines will flow. This is source sink. They will have similar expression for potential. Okay. Now we'll have a small break and we'll invite Shyamala to share something with us.
Sir,
Hmm. Tell something for us, for our benefit or time pass. Just short break.
okay. So
Hmm.
I was watching Fast and Furious 9 a while ago, as
Again,
in
again.
the morning.
What is it? You were?
Fast and Furious 9, a movie.
What's the movie? Passing?
Fast and Furious
Oh,
9.
Fast and okay. Nine.
Yes,
Oh, is it
I
a
was
recent
watching it
movie?
in the morning.
Early morning or during the class?
Early morning, no,
Uh,
like we had 2 free hours during that
oh,
time.
okay. Good. Hmm. What is good about the movie?
I didn't find it very good as of
Hmm.
now. I have just watched some part, like half of the movie.
Okay.
It's a car race kind of movie, action movie.
All this Fast and Furious series is like that, I think.
Ah, yes.
Okay. Okay, good. Okay. Anything else you like to add or?
Yes, we are also doing this anthology as a part of Poetry Club of Shrishti,
Okay.
and it will be releasing in a while, and it would be great if everybody could read that.
Sure, very good. How many of you or it is undertaking this work? You are doing it? Collection part?
Yes, I'm the head of Poetry Club, so I'm there,
Wow.
and
Okay.
we have a team of editors over there. We have collected a few poems, like about 50, and we will be putting it as an ebook.
Sure. Is it what is it? Collection of poems by whom?
Members of Poetry Club, Amrita
Ah,
people,
oh,
students.
fantastic. Worth reading, yeah. Worth reading.
Yes.
Thanks, Shyamala. Thank you.
Thank you, sir.
So let's get back to the lesson. So source sink. So radial outflow or inflow from a point requires source of sink. The phi is known as, given the m is, the mass, you can say it is a mass flux or, volume flux or some constant you can say by 2 pi into ln of r by r naught. This derivation have been done by you earlier. You can revise it. Then vortex, the same potential we given as gamma by 2 pi theta. Vortex is the, you can say it is the other one. It is not, nothing is going inside or outside. Streamlines are just going in circles, pure circles. Okay. So when you combine both these, they will still be solution. When you add these vortex to a sink or so, for example, add these two, you may get a streamline like this. Okay, if you go on a spiral. Intuitively, you can think about that. And the good thing is, this will also be a solution of potential equation. So we make use, we call this as principle of superposition. You can superimpose uh, two potential flow solutions to get another valid potential flow solution. So uniform flow in a plane also has a potential or Vx plus Vy. All these are All these are actually solutions of the Laplace equation, which is given by dou squared phi dou squared phi by dou x squared plus dou squared phi by dou y squared is equal to 0. Known as Laplace equation. You already seen the right hand side is not 0 but function of x and y. What is it known as, Shyamala? I told you in grid generation, just to give you a clue. Name of this such an equation is what? We looked at elliptic grids, which is solution of the Laplace equation. You can not only use for stream flow, you can use this Laplace equation anywhere. Just in electrical engineering, magnetism, so many places it's used. Shyamala, are you there, Shyamala? Yeah.
Yes.
If the right hand side is non-zero, a function of x and y, then the equation is known as
Poisson's equation.
Poisson equation. Okay, very good. Poisson equation. Okay. So we use it for Poisson grids where we want to remember. This has just the equation now. We use the equation for different purpose there for generating grids. Here we are solving it for some other purpose for fluid flow problems. These are different intentions altogether. For example, you can generate a grid using Laplace equation, but just the grid. You can solve any other flow in that grid. For example, I can solve an Euler equation in that grid, which is not at all this equation. It's a different equation. So for purpose of grid generation also you can use. What I mean is the purpose is different. Don't think that if you generate a grid using a Laplace equation, you only solve Laplace equation grid. No. Okay. Some people get this confusion. All right. Then potential function in polar coordinates is given here. Qn and Qt. N is normal mass flux. Qt is tangential mass flux. So these are dou phi by dou r and 1 by r dou phi by dou theta. Not intuitive. Okay. Then in Cartesian coordinate, x coordinate use dou phi by dou x. Then y coordinate v velocity dou phi by dou y. So stream function is orthogonal to velocity potential, which means at every point it's at right angles. To tell you if this is called a stream function of this flow, then at every point the potential will be orthogonal to it. This may be a potential function phi. It will look like this. This is stream function, let's say S or something. At every point there will be at right angle. The angle between at these two at every point is right angle. Here or here, anywhere. Okay. I'm just using it as an example, very simplified example. Even in complicated case, it's true. So Cartesian coordinates, it's easy. X component of velocity is dou phi by dou x, y component of velocity is dou phi by dou. If you know the velocity everywhere, and if you know these, static pressure or stagnation pressure, you know the pressure everywhere. In particular, you know the pressure on the airfoil surface or body surface. You can you can integrate the pressure and get the forces, aerodynamic forces you want. Ultimately, that is the aim of our, CFT, to find the pressure distribution. And if there is a temperature distribution also, and plus some other fluid dynamics variable. So you can assume streamlines as lines of constant stream function across which there is no mass flow. This is known denoted by the vector psi. Instead of s, I will put psi here. So psi is constant. Psi can be a function of x and y. So this will assume so many shape for so many types of flows. Because there is no tangential, no normal flow across a stream function. Suppose if a flow has this as one streamline and this as another streamline, okay. By the definition of streamline, there is no normal flow, which means the flow is tangential. So whatever enters here, this particle will be here in steady state. This particle will be here. In between whatever are there, they will be here. In other words, no mass flow in this direction. So m dot is equal to 0. The normal direction. M dot n I can put normal direction. So this is a very important this one, because if you look at a solid wall, there also there is no mass flux into the wall, out coming no masses coming out of the wall. There also there is no mass flux. M dot n is equal to 0. Another way of telling this is velocity component normal to the wall is 0. We can use the same here also for a streamline. So for practical purposes, you can replace the streamlines by solid walls. Okay. And the flow inside all the fluid inside the streamline will not know anything about it. So, I mean, I want to remind you once more, we are talking of inviscid flow. Whatever we have talked now is true for inviscid steady flow. If the flow is viscous, it's no longer true because velocity will be 0 here and there will be a velocity variation like this. So the streamlines, if you don't have the wall here, the streamline will look it will be different. Okay, the pattern will be different. Although there is no mass flux, the pattern will look different if there is viscosity. So let's not consider viscosity now. Let's consider only inviscid flow. Okay, I think I should stop here. Let's see, we start tomorrow. Yeah, more complex flows by superimposing all the simple flows we can do. You have gone through this already. Yeah. So, any doubts? We can stop the recording. Right? If there are no doubts, we will start the class now.
Sir, in the superimposition, if the source and sink have equal strengths, then they'll cancel out, right, sir? Is it like
Are they
that?
are they at the same point or are they at different points? Who's that? Who's asking the question?
Vignesh, sir.
Vignesh. See, so source and sink is not only depends on the strength. Okay,
Yes, sir.
it depends on where they are placed.
Okay, sir.
You tell me some number. I will draw the. We'll just have that game so you'll understand. Okay. Tell me just some number for source. Tell me.
10.
10. Okay. For sink.
5.
5. Where is it placed? Somewhere here.
Yes, sir.
Somewhere here. 5. So the sink strength is less than source strength. 10 is coming out here, but only 5 is getting absorbed by the sink. So what will happen is the streamlines will flow from here. It will be radially outward, but the sink will actually pull it inward. Okay.
Okay, sir.
So it will be something like this in this case. but then the excess mass will flow outside.
Yes.
Be something like this. Okay. So we'll get a solid object where it stops, and then it may look like this. Understand?
Yes, sir. Okay, sir.
If they're very close together, you will have something like a doublet. You remember?
Yes, sir.
Some is like this. Here it may be like this. Two circles.
Okay. Yes.
Remember?
Yes, sir.
Maybe a doublet. Yeah. If they're very close together or equal strength, that is 5 and 5. If it is 10 and 10, you will have a doublet of a stronger strength.
Yes, sir.
So the mass flux is they may go faster. Same streamline pattern, but velocity magnitude may be faster. Are you getting it now?
Yes, sir. I got it, sir.
Yeah,
Thank
yeah. Any other doubt? Shall we close the class? No doubt.
Yes, sir. Thank you, sir.